and then we give the screen to Marjan Sirjani, who is going to talk about the Agile verification-driven development of cyber-physical systems. Sounds like a big challenge. So please start when you're ready, Marjan. We can see your PowerPoint.
You can, right?
And the presentation mode, it works. Great. Please go ahead.
Okay. So you can all hear me, I hope. Okay, good. So this is, yeah, this is just, I should add a towards to the beginning of it. So this is just the beginning of our work for this Agile verification-driven development of cyber-physical systems. The work is a joint work with many people. The main contributors are Edward Lee from UC Berkeley and Luciana Provenzano from, she was from Bombardier and now she's fully working at our university at MDH. So Christian told me that today we should use examples. So everything should be by running by examples, showing you concrete examples. So that's what I'm going to do. The story is about a door controller in a train. And this is the story that actually we got it from Luciana. She's a safety, and she has been a safety engineer at Bombardier for 7 years. And we got the story from her as a safety engineer. She gave us this safety function. So there is this door controller in a train, and there is this door module that can receive the following messages: open, close, lock, and unlock. And we assume that the initial state is closed and locked. And this is something that we don't want to happen. We don't want bad things to happen. Okay, start from the simple things. We have the driver who is controlling the door module, and it goes passes through a network. The command sent by the driver sends unlock and open, and the door is unlock and open. And also there is a passenger who can uses the external open door button and open the door. And when the train is ready to go, the driver will close and lock the door. The command is passed to the door controller. And of course, we do not want a locked door to be open, because now the driver decides that the train has to start moving. And we also, this is a safety property, and we also want to make sure that the doors are at some point closed and locked so that the train can start running. So this passenger can make some problems here between the door being locked, and before getting closed, the passenger can just open the door and stop the train from running. The other safety property is that do not unlock the door when the train is running. And it can be more complicated than that in a cyber-physical system. So there we can imagine of a train that when we are getting close to the platform, there is some vision system that already unlocked the doors to be fast, to be able to open them. And also there may be a fire detection that wants to open the door if there is a fire. But still we want to make sure that when the train is running, or at least in some situations, the door shouldn't be open. And this lock, actually this lock process or function is to make sure about that. So this is the example. And again, this is the bad situation we don't want to happen. And when I talk about cyber-physical systems, there are different viewpoints for analysis of cyber-physical systems. Of course, we have the definition that we have cyber-physical systems are network embedded computers monitoring and controlling the physical processes. We can also rephrase the same definition and say that cyber-physical systems are systems in which mechanical devices are controlled or monitored by computer-based algorithms. So it depends on which way you are looking at this system. So there are people who work on hybrid automata or continuous systems and doing the verification of cyber-physical systems, what we did, we focus on the first definitions. We focus on the software. Of course, I'm a software engineer, and we focus on the software part and do the analysis and the verification from that point of view. So as I told you, I was working with Edward Lee. So he's at the end of the spectrum, who has been working embedded systems and this kind of cyber physical systems for, I don't know, 40 years. And the other end of the spectrum is Luciana, who is a soft side of software engineering, doing safety engineering. So this is, and we try to, yeah, these are two separate projects, but what I did, I tried to cover the whole spectrum. So this is what we got from Luciana as the safety requirements. Of course, it's a joint work with other people at MDH, like Christina and Kai. So they have this kind of structured requirements. They are giving us this description: given the train is ready to run, when the driver requests to lock the external doors, then all the external doors in the train shall be closed and locked. Given an external door is locked, when the passenger requests to open the external door, then the external door shall be kept closed and locked. Given an external door is locked, when the passenger requests to open the external door shall open if it is unlocked. So you can see that this is the way that they write their requirements, the safety requirements. And from these requirements, we try to extract both the model and the properties that we want to check. And we then make our code, our actor code, to be able to verify it. And we did it in an agile, iterative way. So the way I look at validation and verification, we have this real world problem. We build a model out of that. Then we build our executable program. So we hear from the real world, which is very complicated. We abstract away the details we are not interested in. We build our model, and then we need to add some details to build a program. Also, we have the spec of the system, which are the properties we want to check, like a door must not be open. This is the real world problem that we have, and the model can be state diagram, sequence diagram. We heard in the previous talk, and it can be also a Rebecca model. So what we do, we use model checking. What is model checking? It's a tool. So it's an automated tool that you can just input your property, input your model, and it will come back and tell you if something is wrong. So what we do with this kind of cyber physical systems, what we notice, it took me 1 year, actually less than 1 year, but to convince Edward that model checking is interesting and useful for what he does. He started coding, of course, like a hacker. He started to just code. And then I showed, we mapped the code that he was writing to Rebecca, and we found mistakes. And gradually we started last July, and we finally could write a paper together and could have some kind of agreements in stuff that we can write down. And I can send you the link. Now the paper is out. But anyway, it's not easy because it's full of concurrency. Now that you bring in cyber physical systems, embedded systems, they're used to work with these PLCs and this kind of sequential model. So they have this guarantee that everything can happen in one cycle. But when the network and software comes in and you have this asynchronous communication and events happening, then everything can go wrong. This is one thing, so this asynchronous coming in because of the network, and the other thing is timing. Because we have physical processes, timing is really, and real time is really important. So these are the two dimensions that we have to cover, and testing is not good enough. Very easily, you can just, the mistakes can be just there without you seeing them. Testing or simulation can miss them. So what we did, we started from architecture. Again, this was very good to have my presentation that we saw that there are different model. So we have a kind of architecture or an abstract architecture that we need to use. So there is the passenger, there is the door, there is the controller, and some messages or sensing coming in from the train that the train is ready to leave or is approaching the station. The controller is sending the messages or commands for open, close, and lock and unlock to the door. And there is also the passenger sending the message. And this is the state diagram of the door that can be in unlocked and closed, unlocked open, and locked and closed. And the train that can be approaching or leaving. And then the controller is the coordinator who is actually coordinating all these elements in the cyber-physical system. So the architecture is, of course, more detailed and more complicated, even more complicated than what I'm showing in this slide, but we did some kind of abstraction, and this is, here I'm showing you what abstraction we did. So we put all these things in one actor and named that door, and this is passenger, this is the train, and again, there are some components that we collect them and call them the controller. So this is the behavioral model, and then we have the properties we have to show, and one of the properties is this, that it's not possible to open a locked door or lock an open door. So from the requirements that Luciana gave us, we extracted the state variables that we needed to model or to build the code, and also to write the state diagrams. And from the variables, you can see you have two Boolean variables, and this is the state that you don't want to be in. Open and locked, you don't want to go there. So this is the property, and this is what we want to check. And these are the state diagrams that I have already showed to you. So this is the train and control, the train and the door. And you can see that this is really the controller who is coordinating everything. Train is leaving. And you can see the timing here. So we also model the time. I will show that in the code also to you. So when the train is leaving, then you send the command of close and lock. And then when the train is approaching, you send the command of unlock and open. And passenger can come in, and you have to take care of that. So the process is, if you look at it like that, this is a kind of waterfall, but this is not is really happening. So it is an iterative and incremental and agile process. You get the architecture, you get the requirement, you build your behavioral models like state diagrams and sequence diagrams, and from that you write your Rebecca code. And of course you can jump. So many people can jump from architecture just to Rebecca code or to the executable code. You can skip the behavioral models. It depends on the people who work with this kind of approach. But what we did and what we think is the best is to look at the architecture and requirements and go ahead like this. While you are debugging, you find the problems, and you can come back to any of these and refine them. And even because you're building your code out of these requirements, there are many things that are vague and inconsistent in the requirements, and you can just catch that up front. And you start from small functions. So the scalability and what Jan Bosch always talk about, that you build that small house. So we do it in an incremental way. So we start from small and then we build around that. And we had a kind of compositional approach that hopefully I can show you. Christian, when do I have to stop? My deadline.
Yeah, it's 13:50, but we would also like to have some room for questions.
13:50. So I stop at 13:45 in 5 minutes.
Yeah, that would be perfect.
Okay. Okay. So this is the sequence diagram, the door, controller, and train, and the passenger is not here yet, but you also can add the passenger. And yeah, I already showed you the stuff. So this is the Rebecca code. You have all the entities, all the components that you see in your problem, or the components that you see in your cyber-physical system, you map those to classes or reactive classes like train and the door. And of course, you also, in the next slide, you have the controller, so you can see that. In the train, the events become the message servers or event handlers. Also here, all these events or messages are event handlers or message servers in your Rebecca code, and then the rest is the logic. So this mapping is not complicated, and you have the controller. And in the controller is different. In the controller, you have to receive the data, receive the status of the door and the train, and then you just trigger the events that you want to happen. And here you instantiate your actors, like the door, the controller, the train, and also there is an external or the environment, who is the passenger, who is just pressing the door open. And using Rebecca, you can check this assertion. So there is an Eclipse tool that in one of the slides, you see the interface that you can input the model, you can input your assertions and the property that I talked about. And Rebecca the Afra tool, this is the tool. So here you put in your model, and there is also the property file. Here is the property file, the assertions like door, not door closed and door locked at the same time. And then you run, you just press the run, and the tool will come back and show you if the property is satisfied, or if there is a counterexample and assertion failed. So here the assertion failed, and you can see why it's failing, because here the door is closed and locked, but door open could happen. So the assertion is failed, and you see that there is a bug in the code, and you see that you can get to this state of locked and open that you didn't want to get there. And so you just refine your code and correct it. You add some if and else's in the code, and then the code is correct. And talking about incremental iterative, Luciana was talking about the train is a running state, and we didn't even consider that. But now that everything is okay, we debug the model, you add the running state, and then you check it again. So, and here then you can check that the train is running, and the door, when the train is running, the door is not open. So, and the train is running, the door is not unlocked. Again, you can check this with Rebecca. The other thing that you can check, the progress property that I told you. So if this passenger is very persistent, just pressing this open button, and you can check your timing issues. You can check your timing configuration, the network and the reaction delays, and see how this can happen, that the passenger doesn't really allow the door to be locked. The door is closed, but then the passenger opens it, and so the train can never run. So for finishing the loop, I can't remember what I showed you last report workshop, but anyway, now we have Lingua Franca language in place. So before we were just up to Rebecca. Rebecca is a code, so it's a code like language, but it's not executable. It can be mapped to Java, but it's not executable now. But now we have Lingua Franca, which is a language that Edward Lee is building in his group, and they are writing the body of each reaction. The body of those message servers, handlers that I showed you, can be written in different languages, including C and C++. And this is the, actually this is a diagram, a structured diagram that is derived from the Lingua Franca code automatically. Here you can see that you see the controller. I didn't write the train here, but you have the controller, you have the door, and you can see all the events. And Lingua Franca is, the semantics is basically, if you don't look at the C part, The semantics is just Rebecca. So mapping Lingua Franca to Rebecca is 1-to-1. We needed to add priority to Rebecca to be able to do that, which was easy. We just removed the non-deterministic part, and it actually was good to shrink the state space also. So now you can build the code and you can execute the code, and Lingua Franca is built for CPS languages. And one more thing that I can tell you is that when you build your Rebecca code and you do the model checking, it will come back and show you the whole state space. So it will show you where you can go. From train not moving and door unlock, you can go to different states when different events are coming in. And it will show you that at some point you have train is moving and the door is unlocked. And this is the property that you don't want to happen. So if the semantics of if you have a platform and the semantics of the language is guaranteeing that you have a kind of PLC kind of execution, that you never see these intermediate states, then you're fine. So you're jumping from this state to this state and then to this state, and you don't need to worry. But if you don't have that kind of sequential language and guarantees, then you need to be worried about this event-based semantics and use model checking to find the problems. The other example is this kind of timings that I showed you here. There can be physical or external events coming in, like this is the passenger here. And this can introduce design problems, and this is again what Rebecca can catch. And what we did by putting all these things together, working both with Edward Lee and with Luciana, what we did, we tried to have it close to both communities and make it accessible to both and useful for both. So there is an iterative incremental approach. In the paper we showed, in the paper with Luciana, we showed different increments and how we disambiguate the requirements. We showed that the mapping is not yet automated, but the model checking is of course automated. With the work with Edward, we showed the different semantics and implementation platform and how they can affect the code and the outcome. So I think I'm done. And this is our language and homepage.